All right, so we are ready for the last section in Chapter 2, 2.6. And then after this section, we get into some of the calculus stuff. We'll start limits and get into all the things that we should actually be learning in this course. But before that, let's talk about exponential growth and decay functions. And then later in this section, we'll get into some financial math. So exponential growth and decay, we're going to let y naught be the initial amount. So the amount at time equals 0. The quantity is said to grow or decay exponentially if, for some constant k, the amount present at time t is given by this function. So we have y equals y naught e to the kt. So y we're going to let represent the end amount, or the maybe better would be present amount. So present at time equals whatever it is. So t equals 10 or t equals 20. But obviously we can still keep going after 10 or 20. So present amount, we'll call it that. Y naught is the initial amount. K is going to be the rate. And then t is going to be time. And of course, e is going to be the irrational number that we've talked about before. If k is greater than 0, this is going to be a growth function. And if k is less than 0, it's going to be a decay function. And of course, growth means that the graph will look like that. Decay meaning it will look something like that. Okay. So nothing too complicated about these formulas. You certainly want to be sufficient and competent at solving exponential equations. That's the main skill that you will need. So let's look at the first example. So we have yeast in a sugar solution growing at a rate such that 5 grams, so that is going to be our initial amount, y naught, grows exponentially to 18 grams, so that's going to be our present amount or ending amount, after 16 hours. So there is our t. So find the growth function, assuming exponential growth. All right, so here's our initial amount. Here is another point, a data point. So at t equals 16, we have 18 grams. So that is an ordered pair, 16, 18. So the ordered pair ty. And so we need to find this formula, or this function, y naught e to the kt. So y naught is 5 grams. That's our initial amount. So y equals 5e to the kt. So we need to find k. That's essentially the two things we need to find, y naught and k. We're given y naught, so we also now need to find k. So now we have a t and we have a y, a data point here, ordered pair. So let's plug those in, and then we should be able to solve for k. So we have an exponential equation here. We've seen some of those before. So let's divide by 5. And so 18 divided by 5 is 3.6. So 3.6 equals e to the 16k. Now we have a very basic exponential equation. Let's ln both sides. Ln and e cancel out. Let's leave this for just a second. Put that in the calculator in a minute. And so we have ln of 3.6 equals 16k. So now let's divide by 16. We can put parentheses around that just for clarity in the calculator. So when you put this in the calculator, so k equals ln of 3.6 over 16. So when you put this in the calculator, you put ln in the calculator, opens parentheses typically. So you want to close the parentheses and then divide by 16. So when we put that in, we get an approximate answer of 0.08. And that'll be rounded off, but that is good enough. So 0.08. So that is our rate. And so then our function, so we're asked to find the growth function. So the growth function would be y equals 5e to the 0.08t. And then that will be our final answer there. Okay. Probably have a couple of decay examples in the homework. Be the same thing. You'll end up with a negative rate for those, but very similar in how you do them. All right, so let's talk about some financial math. So, effective rate for compound interest. So R is the annual stated rate of interest. M is the compounding periods per year. The effective rate of interest is given by this formula here. And so M is the compounding periods per year. So that means things like if you're compounding quarterly, M equals 4. If you're compounding monthly, M equals 12. If you're compounding daily, M would be 365. If you're compounding annually, M would just be 1. And so it's really just a matter of remembering this formula, plugging it in. So not a big deal. If the interest is compounded continuously at a rate of R, annual rate of R, the effective rate equals e to the R minus 1. All right, so easy enough. Let's look at a couple of examples. So we have 4.25% compounded monthly. We need to find the effective rate, so we're just going to use this formula here. So R is 0.0425 and M is compounded monthly, so M will be 12. So we have the effective rate is 1 plus 0.0425, M is 12, raised to the 12th minus 1. And you can probably put this in all at once. Be a little bit careful, but it's not too complex that may make a mistake. And so we get 0.0433. So now, one thing, it's always good whenever you can, if you're solving a word problem or any problem really, but it's particularly relevant with word problems, you should be able to maybe most of the time have an idea of what the answer looks like. And when you're doing these effective rates, your answer is always going to be close to the rate that you're given. So the effective rate is always going to be pretty close to the annual, monthly, quarterly rate, whatever it is. So just keep that in mind. If you get something like, 62% for your effective rate, you probably did something wrong, because your given rate's probably not going to be anywhere near that. So just keep that in mind. Your answer here should be close to the rate that was given, but not going to be exact, or not going to be the same. The only way it'd be the same is if you're compounding annually, in which case there's no point in doing this problem. All right, compounded continuously, so we're going to be using this. So R sub E equals e to the 0.0375 minus 1. And again, you're going to want to make sure this minus 1 is not in the exponent. So depending on the calculator that you're using, just be careful with that. And again, we get something close to the rate that we're given, 0.0382 in this case. Okay, so no big deal on those. Those are just basically plugging the numbers into the formula and go. Okay. So now we're going to need another formula for this. So third example, find the time needed for $30,000 to grow to $50,000 when invested in an account that pays 3.15% compounded quarterly. So the formula we need for this, we're basically taking that effective rate formula and putting it times the principal, and that will give us the accumulated amount. So A is accumulated amount. We'll write present amount or ending amount. P is, we'll put ending here also, ending amount. Initial amount is P. R is the rate. M is compounding periods per year. And then T is going to be time. So how many years are you going? We'll say time measured in years. Okay, so what are we getting? So find the time. We are looking for T. $30,000 is your P. That's your initial amount. We need that to grow to $50,000, so that will be your A. And then, of course, 3.15% is going to be your R. And then quarterly means that N equals 4. So we have 4 compounding periods per year. All right, so now just plug everything in, then we're going to solve for T. So 50,000 equals 30,000 times 1 plus R is 0.0315. M is going to be 4 raised to the 4T. Okay, so this looks pretty complicated. It's really not much different than the typical exponential equation that we've been looking at. So first, let's divide by 30,000. So we get 5/3. We'll just leave that the way it is for a minute. 1 plus 0.0315 divided by 4 is 1.007875 to the 4t. Now, this is an exact number. It's not rounded off at all. All right, so now we have a very basic, as far as the form, exponential equation. It looks a little bit more complicated. We got this fraction, we have this decimal, but it's just some number equals some number raised to an exponent. So no big deal. So how do we solve that? We take the log on both sides. You can do ln or you can do log. Either way, it doesn't matter in this case. So ln of 5/3 equals ln of 1.007875 to the 4t. Then let's not put anything in the calculator yet. So let's use our log properties and bring this exponent in front. And then we can, 7/5, we can just divide both sides by 4 ln 1.007875. Divide both sides by 4 ln 1.007875. Okay, so now t equals ln of 5/3, put parentheses around that, divided by, now maybe put parentheses around this in the calculator. If you want to do it all at once. You don't really have to, maybe not recommended. And so, like I said a minute ago, it's a good idea to have an idea of what your answer should be. In this case, it's a little bit tricky. I mean, I wouldn't bet on getting a big value for t, meaning like t is probably not going to be hundreds of years or thousands of years. It's probably going to be somewhere between 10 and 30 years. I mean, generally speaking, for problems like this, that's a good range for an answer for you to expect your answer to be. Getting any more, and that's just kind of based on experience. It's not really looking at the numbers. It's just doing a bunch of these problems, and that's typically where the answer is. It could be less than 10. Obviously, you're not going to get a negative answer. And I would not expect a huge answer, like time to be like several decades, or hundreds of years. So let's see what we get. So we get ln of 5/3. And the way I do this, ln of 5/3, put in equal, now divide by 4. You'll just take that answer, divide by 4, and then divide by ln of 1.007875. And we get 16.3. So 16.3 years. Okay. So that's the answer. That's a good rounded off answer. Now, a common mistake I see, and you're in calculus, so maybe you don't have this problem anymore. Maybe you're beyond this, but just in case, a common mistake I see in problems like these is rounding too much and too early. So let's do this the wrong way. So we'll draw an arrow here. We're gonna diverge here. I'm not going to follow this way. We're going to go to here and then go this side track that you should not go on. All right, so this just kind of show you the common mistakes that I see students make. So let's put ln of 5/3 into the calculator. And we get 0.5108256,238. So it's an irrational number. Let's round that off at 0.51. Bad idea, but let's do that. equals, now let's bring the exponent down, 4t ln of 1.007875. So we get 0.51 equals, now let's put 4 ln 1.007875 into the calculator, and we get 0.0313766161. So let's round that off at 0.03. Terrible idea. All right, so 0.51 divided by 0.03 is 17. So it's actually not as far off as I thought it would be, but you still get this wrong. So if you put in 17 and you get exactly 17, that's not 16.3. And the reason is you're rounding off here. So rounded. So that's rounded. And then this is the exact answer, but that's because you rounded so much that it just happened to end up that way. So the point is, don't round off at all if you can avoid it until the very end. So here you can round because you're at your final answer, but general rule, do not round until the final answer. Now, sometimes it's not practical to not round. So if you must, round at six decimal places. If you round off at 6 decimal places, you will almost never go wrong. If you never round at all, you won't go wrong. So just a little tip as you go through, and this mainly applies to application problems like this where you're multiplying and dividing decimals. Typically, when you're just solving equations, it doesn't matter too much, but on these application problems, a lot of times it does. All right, last one. Find the interest rate that will cause 3,200. So there is our P to grow to 4,500. There is our A in 7 years. There is our T. Compounded continuously. So compounded continuously means we're going to have an E in our formula. So A equals PE to the RT. And so we're finding the interest rate. So we're looking for R. So 4,500 equals 3,200. E to the 7R. So let's divide by 3,200. And so 4,500 divided by 3,200 is 1.40625 equals e to the 7r. Now that's an exact answer. That's 5 digits, but that's an exact answer, so it's okay. ln both sides. Now when you start getting to ln's, leave the ln's. Don't put those in the calculator till the very end. All right, ln of e cancel out, so we get ln of 1.40625 equals 7r divided by 7. Probably need parentheses around this. And so then we get, again, know what your answer should look like. Your answer is probably going to be less than 0.1. And it is. Now, if you get an answer more than 0.1, that's not necessarily wrong. If you get an answer of 0.8, 0.9, or more than 1, that probably is wrong. So just be aware of what answer should look like. And if you get one that doesn't look like what you expect, but it's still possible, then just check that you set everything up right. Because it's possible to get extreme answers, but normally you don't get extreme answers. Normally you get reasonable answers. So R usually is between 0 and say, we'll say 0.15. If you get above 0.15, you're getting a little bit, aggressive growth, we could say. And you could also go in the negative direction too. We won't cover negatives here too much. But just as we go along, as you see application problems especially, keep in mind what are reasonable answers. Okay, so that finishes up chapter 2. Next section, we get into chapter 3, we get into limits and the actual calculus that we're going to be doing.